Okay, so today we're going to continue with implicit differentiation. Last time we focused on the fact that y is treated the way u would be treated in using the chain rule, but otherwise implicit differentiation is just the chain rule. Last time we also looked at exponential and logarithmic functions and their derivatives, with the derivative of e to the x being e to the x and the derivative of ln x being 1 over x. This time we'll really take advantage of this fact by using the very powerful technique of logarithmic differentiation. The next couple of classes after will have really interesting applications. Related rates is the chain rule again, and the applications will largely have to do with maximizing and minimizing values of functions. So for question 316 in the section on implicit differentiation, we're asked to analyze the curve of points that satisfy this equation. So there's a picture of it here. We're asked to focus specifically on the point where x equals 2 and y equals 1. Just for the sake of curiosity, I want to check that this point really does satisfy this equation. So 2 times 2 cubed is 16, 2 times 1 cubed is 2, and when we subtract 9 times 2 times 1, we really do get 0. So we're looking at a point that really is on the curve. And the objective of the question is to find a straight line that is tangent to the curve, which really means if you're on the curve, but you're only interested in some nearby points, can we use a straight line that gives a good approximation for the curve just in that region? Right? So that's what the equation of the tangent line will do for us. And if we're only interested in points really close to x equals 2 and y equals 1, maybe instead of using a really complicated expression, we can use a simpler one like the equation of a line. So we take the given equation and differentiate both sides with respect to x. Okay, so the right-hand side is the easier side, so I'll do that first. The derivative of 0 is 0. For the left-hand side, the 2x cubed part has a derivative of 6x squared. For 2y cubed, we differentiate with respect to y, we get 6y squared, but we're not differentiating with respect to y, we're differentiating with respect to x. So by the chain rule, we multiply by dy by dx. And so now I'm going to do this a little differently. To make math easier, replace all subtraction with addition. We're going to add the derivative of the product, negative 9xy. So the way the product rule works is that we identify this as the product of two pieces, and we put them in these brackets, differentiate the pieces like so. So now for the next step, we put all of the dy dx terms on one side of the equation and kick all the others over to the other side. So the negative 9y becomes positive 9y right from there, and the 6x squared becomes negative 6x squared. Now really, the reason we're putting all the dy dx on the same side of the equation is because we want to know how much of it there is, so that we can divide both sides by how much of it there is, that is to say the amount in the bracket. So there's 6y squared subtract 9x of it, and I would really say you can go directly from that top line down to here. If you know that you're counting how much dy dx is there, just put that amount in the bracket. So now we have a formula for dy by dx. Like so. Okay, so I've put a little reminder here of what the actual question is. We're interested in the equation of the tangent line at a specific point where x equals 2 and y equals 1. We have a formula for the derivative anywhere on the curve, but what we want to do is take the formula and plug into the formula x equals 2 and y equals 1. And when we do that, well, 9 subtract 24 divided by 6 subtract 18. Both the numerator and the denominator are negative, so I'll cancel those. We're left with 15 over 12, which is 5 over 4. Now 5 over 4 is a little bigger than 1, and in the picture here, the slope of the line looks a little bigger than 1, so this at least seems reasonable. Now to answer the question, we're looking for a straight line with slope 5 over 4. That's what we just found. So y is equal to 5 over 4x plus I'm not sure what. But we have a point on the line, right? So the point is both on the curve and on the line. So we can check, right? When y equals 1, x equals 2. 2 multiplied by 5 over 4 is 5 over 2. The 2 from the x would cancel from one of the 2's in there. So 1 is equal to 5 halves plus, well, negative 3 halves would work, which means we have negative 3 halves. So the answer to the question is that y is equal to 5/4 x, subtract 3 halves. There's your equation of the tangent line. So I realize that some people would be more comfortable writing y equals 5/4 x plus b, and then setting up an equation by plugging in the point and solving for b. But that seems like a lot of work. If you can get the answer without following a bunch of steps, then just do so. This has the advantage that it checks the answer as well as finding the answer. Okay, next we're moving on to section 3.9, and we're going to talk about logarithmic differentiation. First, just to motivate it, last time we found the derivative of the function log of the square root of 2x minus 1. The question was simplified significantly by realizing that the square root meant we were taking something to the power of a half, and there's a law of logarithms that allows us to pull the half out front. So I'm not going to redo this question here. I'll just mention that this idea that the laws of logarithms can help you has a lot of promise. So next I'll show you how it works on a question where you know the answer. Okay, so suppose we want to differentiate x cubed. Well, you know the answer. It's 3x squared. So we're using this example to show how the method of logarithmic differentiation works. The first step is to take the natural logarithm of both sides. The reason we're doing this is because we want to artificially use the laws of logarithms to help us. So we've set this up just so that we could pull this 3 out in front. So we have log y equals 3 log x. So we have ln y equals 3 ln x. Next we differentiate both sides with respect to x. To differentiate the log of y, well, it's 1 over y, but then we need to multiply it by dy by dx. Right, so we're using the chain rule because we're differentiating with respect to x. The chain rule says go ahead and differentiate it with respect to y first, but then multiply by dy dx. The right-hand side is 3 over x because the derivative of ln x is 1 over x, and then we multiply that by 3. And now for the last step, we multiply both sides by y. But of course, y is equal to x cubed, so that's where we started, and an x cancels, and we're left with 3x squared. And we knew that the derivative of x cubed was 3x squared. So this was an example where we knew the answer. Okay, next example, y is a product of two functions. Always works the same way. We take the log of both sides. When we do that, we take the log of this product. The reason we're introducing logarithms when they aren't already there is because we want to take advantage of the fact that the exponent required to get to a product is the sum of the exponents of the factors. Now we differentiate both sides with respect to x. The left-hand side is always going to look the same. We're differentiating with respect to y first, but then by the chain rule, we have to multiply by dy dx. The right-hand side, well, the derivative of ln x is 1 over x. To find the derivative of ln sine x, use the chain rule. Think of it as ln u. 1 over u would be the derivative if you're differentiating with respect to u. But then multiply by du dx, which means multiply by the derivative of sine x. Okay, so to fully answer this question, we have to remember what y is. So y was equal to x sine x. So that means when we multiply through by y, so we see some cancellation here. The x and the 1 over x will cancel. So we'll get sine x for the first piece. And for the second piece, we'll have x cosine of x. So that's our derivative. And if you were to use the product rule, you'd get the same thing. You'd have the two factors, an x factor here and a sine x factor there, and then you'd have to differentiate across. So hopefully you can see that the product rule would give you the same thing. And in fact, the product rule really comes from logarithmic differentiation, or at least we can think of it that way. So we'll do this a little faster. We take the log of both sides. We know the reason we're doing this is so that we can use the law of logarithms that allows us to replace an exponent with a sum of two other exponents. So that's why we have this. We're differentiating both sides with respect to x. We always get y prime over y. When we take the derivative of the log of something, well, the something ends up in the denominator, and its derivative ends up in the numerator. That applies to g just as easily. And now finally, to find y prime, we multiply through by y. which is f times g. And see what happens if we were to multiply this out. The first term would have an f canceling with a division by f, and you'd be left with gf prime. And for the second term, you'd have a g canceling with a 1 over g, and you'd be left with an fg prime. So hopefully you can see that this is the product rule. Okay, so far all the examples we've done have been examples where we didn't need logarithmic differentiation. This time we do. Take the log of both sides. The reason we're doing this is so that we can use one of the laws of logarithms. So this is how we rewrite it. Really not sure how to differentiate this function without logarithmic differentiation. From here, we differentiate both sides with respect to x. As usual, we get y prime over y. For the right-hand side, we'll need the product rule. So one factor here, one factor goes there. Differentiate the easy one first. The derivative of x is 1. The derivative of ln x is 1 over x. So y prime is now equal to y multiplied by whatever this is. Well, it simplifies a bit. The x and the 1 over x combine to give you 1. And then we just have ln x. And there's your answer.